In this sequence, we will cover damped second-order systems. So before we begin, I wanted to caution you that there's going to be a lot of math here, a lot of theory, okay, that I will take you through. I want you to stay with me. It's going to be very grubby and very grungy, but hang in there. It turns out that all of this theory and math that you will see in this sequence is largely for your cultural background, all right? You really won't be responsible for it in your tests and homeworks and so on. However, it's really important to know where certain things come from. So despite all the math and grubbiness, there will be one point in the lecture where you will hear the word or words characteristic equation. I want you to really perk up and pay attention at that point. The amazing fact will be that despite all the math, despite all the theory, despite all the differential equations, what we really need for circuits analysis is something extremely simple. Okay, and towards the end of the sequence, I will show you that one simple little thing that you need to know, and from that you will be able to more or less predict the entire behavior of these second order circuits simply by understanding the characteristic equation, okay, and how that comes about. Okay, so hang in there. Let's get started with this section, and watch out for when we get to characteristic equations. From there, things will become extremely simple. Now, let me start with a quick review. In the last sequence, we did the example of a pair of inverters that looked like this. So this was node A, this was B, and this was C. And I showed you the following equivalent circuit for those inverters. And we said that if I applied voltage A at the input of the first inverter, and if I try to speed up node B by turning on switch S, and have a small resistor 50 ohms in parallel with the 2 kilo ohms in order to speed up my circuit, I said that what I observed was a waveform that looked oscillatory like this. And all that we have seen so far does not quite prepare us for this. We did look at LC circuits in the last sequence, and we saw some sinusoidal behavior. Okay, but we didn't quite see this kind of decaying sinusoidal behavior, and we will see why that is so in today's sequence. Now, in the last sequence, we also learned that when you have a loop like this, there is inductance associated with the loop, and we modeled that as a little inductance L. And the relevant circuit, okay, to analyze, to understand this kind of behavior was given by this. So here was my 5 volt supply, and here's my 2 kilo ohm or 50 ohm resistors, depending on, it's actually 2 kilo ohm in parallel with 50 ohm resistance. And here was my inductance L, and then I had a capacitance CGS here. Okay, and this was my node B, and this is where I picked my ground node. So this was a second order system. In the last sequence, we analyzed a simpler form of a second order system without the resistance. Okay, just a straightforward LC circuit. Now what we're trying to do is trying to understand where this kind of oscillatory behavior comes from and try to understand the dynamics of that behavior. Okay, and if you want to go and take a look at the demo I showed you for a pair of inverters in the last sequence, you can go back and review that. Alright, so in the last lecture we started by analyzing the simpler LC circuit without the resistance. And here is what we studied: voltage VI, inductance L, and a capacitance C. Capacitance C, inductance L, and node with voltage V, and this was my current I. So we said let's start by analyzing that, and in doing so, the first step, we wrote the differential equation that governed the dynamics of that system. We wrote the equation for node V, the node with the voltage V, and that was given by d squared V by dd squared. It was a second order differential equation. 1 by LC V equals 1 by LC VI. And we said, let's go ahead and solve this for input that looked like this. And this was T, and we said, let's take a step. Voltage, this is for voltage VI, take a step that goes from 0 to capital VI. Okay, so this input could be represented as VI U of T, where U of T is my unit step. Now the reason this input voltage, capital VI, reasonably modeled the behavior of the second order circuit was that, notice when the MOSFET turned off, when the MOSFET at the gate of inverter 1, so this was my MOSFET and this was node B. So when this MOSFET turned off, then it was as if, and if node B was close to ground, okay, was close to 0 volts, well, let me be more accurate here and say close to 0 volts. And then suddenly what I did was, instead of having this input connected to ground, I suddenly turned the MOSFET off, and it is as if a 5 volts appeared at this node that caused the node B to charge up. Okay, so I could model that at time t equals 0 going forward with a capacitance with initial voltage V of 0 equals 0. Notice that I started out the world with the capacitor here. So this was CGS, okay, CGS. Okay, I'm just simplifying, simply calling it C here. So the capacitor started off with voltage 0 volts across it, and my current was also taken to be, so the capacitor was taken to be 0. Okay, this is what we call the zero state response. And then we said the capacitor had input voltage, or voltage across it 0, I have no current flowing in the system, and then at time t equal to 0, boom, I apply a 5 volt supply through a 5 volt supply to the capacitor. Okay, and in the simplest example, I was building a circuit where the resistance was 0. Okay, so the 5 volt supply would appear across the would go ahead and appear across the inductor and capacitor. Here was my inductor with inductance L, and that would appear across the inductor, and then that would give me the dynamics that would characterize a LC circuit. Okay, to recap really quickly, in my LC circuit, here is my input VI, inductor L, capacitance C, ground node, voltage V, current I. Okay, I started off with both V of 0 equals 0 and I of 0 equals 0. Okay, and then I said at time t equals 0, VI took a step input to capital V, capital I, and I needed to figure out the dynamics of the circuit at the node V. Okay, and this would reasonably capture the situation with the inverter driving node B. Okay, at time t equals 0, both the capacitor had a voltage 0 across it, the current through the circuit was 0, and at time t equal to 0, I'm told that I have a 5 volt supply, and so therefore we can go and figure out what the voltage was going to look like. All right. Okay, then the last lecture, we looked at this LC circuit, and then we obtained the total solution for this little circuit, and the total solution was given by V of t, and we got this by solving the differential equation that governed the dynamics of the system as Vi minus Vi cosine of omega naught t. Okay, where we found that omega naught, okay, we found the square root of LC in the system, and we said let's term that omega naught. Okay, so this frequency here is the is called the undamped natural frequency. Okay, and you'll find out why it's called the undamped natural frequency in shortly. Okay, omega naught is sometimes also called the resonant frequency of the circuit. So this was the equation that governed the circuit, and we could plot a response like so. So this was 0, and let's say this was Vt. For an input given by, so this was T, input Vi given by this, so 0 to capital Vi at time t equals 0. So the corresponding input, the corresponding voltage at at V was given by the following. So this is Vi and this is 2 Vi. We found that the response looked something like this. Okay, it was a sinusoidal response, and with frequency governed by the resonant frequency omega naught, which was 1 divided by square root of LC. Okay, so we observed a couple of interesting facts about this response. One was that even though my input just went from 0 to capital Vi, notice that the response at the capacitance was twice the input voltage. Okay, so don't be surprised if you see voltages that go way higher sometimes than the input voltage. Further, you see some very interesting kinds of behaviors such as sinusoids and so on. Okay, these are quite a bit different from what you saw in previous sequences where you saw rising and decaying exponentials.